Okay, gang, today we're doing hybridization and orbitals and then the bonds that go with them. So I know that this is kind of a weird topic, but we're just going to go through it step by step and everything builds on each other. So I really suggest that if you have questions, and put them in the comments so that you get one thing, you can move on to the next thing. So when we talk about hybridizations, we really want to focus on carbon because carbon is a major part of organic chemistry. And in class, we talk about how there are the three major shapes that carbon likes to stick to because it's just what best fits in our world. These are the three shapes that we're going to focus on today. And these shapes depend on the number of substituents that carbon has around it. Substituents just means extra. So I feel like we've all seen some methane, some CH4 gas. These hydrogens are all substituents, so keep that in mind in the future. This is a tetrahedral shape. I'll draw them in a second so that that's also more clear. Gonna move this over a little bit. Okay, so tetrahedral, just like how I just drew, is actually not this shape. This is the planar view of tetrahedral. And the reason that it doesn't actually look like that is because the hydrogens are on the playground second grade and they don't want to kiss. So they want to be as far away from each other as absolutely possible. And they do this by arranging in this little 3D shape. And when we think about how the shape actually looks in person, I'm sorry, it keeps focusing on my hand. This little dashed line means that it's going into the paper, and this little wedge shape means that it's coming towards you. So if you think about it, it's kind of twisted like this, where we have this facing towards us, this going into the paper, and then these are by themselves on the side. So just not super important for this video, but just keep that in mind. And now we're also going to draw our trigonal planar. Trigonal planar is 1, 2, 3, so like trig. And we don't like to mess with these. This is the planar view and the real life view because these are already as far apart from each other as possible, kind of in the formation of like a peace sign. And now we're going to draw a linear, which just looks like this. And these angles are not super important, but for the purpose of the video, I'm just going to explain what they mean. So this is 90 degrees. Think about like a big box. 4 corners, 90 degrees. This one, when they're stretched out in that little cute little not gonna kiss formation, they are actually at 109.5 degrees. And that's just the way that God made it. We've got our 120 degrees, and then we've got our 180 degrees. And these, I like to think of them as the 4 golden numbers of angles in organic chemistry because this is what my teacher said to memorize, so this is what we're going to memorize. And after we get this done, I really want to stress that the substituents are what change these angles and change the shapes to these. So as we keep going, we're going to talk about how exactly these make sense with everything. So carbon by itself has this kind of electron configuration. Electron configuration is kind of like a Gen Chem 1, Gen Chem 2 kind of concept because we've got these different shells that carbons can hang out in. We've got 2s and 2p. That's what we're really going to focus on. And carbon has 4 valence electrons, and that's just because of its position in the periodic table. If any of this sounds kind of foreign to you, then totally comment and I'll explain why that is what it is. But carbon has 4 valence electrons, and we move our way up on these shells, and we put 1 electron in at a time. So God, actually not God, but this man, Linus Pauling, was like, hey, we can't do it like this because these are on different energy levels, which is very true. So he said, well, we should make this on the same energy level. So he just kind of combined them, where if this is like super high energy and this is a lower energy, he just kind of evened them out in the middle, where we've got 4 on the same level, and he hybridized them, completely made up word, so don't let it scare you, into an sp3. because we've got 1, 2, 3 P's and 1 S. So he said, okay, I'm gonna call this sp3. And he just said, okay, we're gonna put him right here. And also, remember that when carbon has 4 valence electrons, that is also linked to its substituents. So when we talk about sp3, we're talking about this carbon right here. Actually, I'm gonna draw it and it's like tetrahedral shape. So it actually is talking about this, where we have 3 substituents, because if there were a different number of substituents, this would not be the same hybridization, and we'll go over that absolutely right now. So when we talk about a structure like this, carbon still has substituents, and yeah, they're not all hydrogens, so that still doesn't affect how the substituents work with hybridization. So this is 1, 2, 3 substituents, and now we're looking at how that affects the hybridization of carbon's valence electrons. So normally it would be the same thing. It would be 1, 2, 3, 4 in the carbon realm, but since we've got 3 attachments, we're taking, I'm just redrawing this right here. We've only got 3 substituents, so we're taking these and hybridizing them, just like how we did in the first example, but now we only have 3 substituents. So we're talking about, instead of sp3, it's going to be sp2. And I know that you're thinking, wait, this has 4 substituents, so why isn't it sp4? The reason it isn't sp4 is because technically one of these is an S, and 3 of them are P's, just like how we've got 1 S and 3 P's. So for this one, we have 3 substituents, but we've got 1 S and 2 P's that are hybridized to be like this. So we have, pretend that this is a little 1 right here, and then we have 3. So this is actually 3 substituents. And what about this P? It's just leftover. We'll worry about that later, but right now the important thing to recognize is that 3 substituents, 1, 2, 3, gives you an sp2 orbital. And for linear, it's basically the same thing, where we have this carbon right here, instead of having 1, 2, 3, 4, it is actually going to just turn into a different orbital. Remember, this is the original shape. Since we only have 2 substituents, 1, 2, we're going to take these 2, hybridize them, and now it's going to look like this. And now this is sp, because we've got 1 S right here, 1 P, and hybridized, and now we've got an sp group, 1, 2. And these p orbitals, they're just going to hang out up there, but do keep in mind, we've got 2 SPs. We've got 3 sp2s, and we've got 4 sp3s. Okay, so I'm going to stop the video because it's getting to be about 10 minutes long, and we're just going to do a really quick overcap of what all this means, because this is hybridization at its lowest point, and then in the next video I'm going to do some examples. So hybridization, carbon by itself looks like this. It's just the way God made it. Carbon looks like this. But my guy Linus Pauling was like, hey, when we make carbon do its little thing in its shape, we did shapes up here, it needs to all be on the same energy level. So he hybridized these levels, hybrid to make them all look at the same level, and he put all 4 of these, since carbon has 1, 2, 3, 4 substituents, into the same energy level. And this is 1 S and 3 P orbitals. So he called it, okay, we're going to call it an sp3. This imaginary 1 is still valid for all of these examples. So when we move to carbon molecules that only have 3 substituents, 1, 2, 3, he said, well, we can't circle all of these because we've only got 3 substituents. So he hybridized only 3 of these and made it an sp2 orbital. And we've got 3 of them because we've got 3 substituents. I forgot to mention up here, but we have 4 of these orbitals because we have 4 substituents. Similar to this one, we have 2 substituents, so we've got 2 little electrons doing their thing, and we've got 2 of them, because technically it goes on either side. So that's why we have 2 of this orbital, we have 3 substituents, so that's 3 of this orbital, and we have 4 of these, so that's 4 of this orbital. So I'm going to upload this video, and I'm going to do some examples in the next one of counting pi bonds, counting sigma bonds, and basically just doing a recap and a little bit more pictures in the next one of how all these hybridizations work with orbitals and identifying them. Hope it helps.